Practice problem 32 on page 106. I'll read the problem. It says, a tennis ball is thrown straight up with an initial speed of 22.5 meters per second. It is caught at the same distance above the ground. A, how high does the ball rise? And B, how long does the ball remain in the air? Hint, the time to rise equals the time to fall. Can you show this? And I will actually show that. So let's do given, find, and solve. So here's the ground. And here we have someone throwing a ball. And they throw the ball straight up from their hand. And it says the initial velocity is 22.5 meters per second. And it's going to go straight up and straight down, and they're going to catch the ball at the same height above the ground. So what that means is that we can treat this as the origin. I'm going to treat this as the origin of where we're going to measure, the location of the ball from. We also know what the acceleration is. It's negative 9.8 meters per second squared. Now, it didn't state that in the problem, but for free fall problems, unless you're on Mars or something, you can assume that that's the acceleration of your object. We're ignoring air resistance. And another thing that's not stated in the problem, but you need to know in order to solve the problem, is that when the ball is at the very top of its flight, it's reversing direction. And if you reverse direction, at the instant you change from going up to going down, your velocity must be 0. Okay, now what do we want to find in part A? We want to know how high does the ball rise, and I'll call that delta y. And then in part B, we'll say how long does the ball remain in the air, or in other words, time. Time in the air. Okay. So I'll solve it down here. Well, look at what I know and what I'm trying to find. I know the acceleration. I know the initial velocity. I know the final velocity. I want delta y. I don't know time. It's not given, and I don't really need it yet. So I look on my list of kinematic equations and find the fourth kinematic equation that says V equals V naught plus, I'm sorry, that's not the right equation. V squared equals V naught squared plus 2a delta y. And so I just need to solve for delta y. And it's going to be v squared minus v naught squared over 2a. Then I plug in what I know. My final velocity is at the top. That's going to be 0. My initial velocity is given to be, whoops, come on, Lake. 22.5 meters per second. You have to square that. Now notice that where I'm squaring this, I'm squaring positive 22.5. This negative is outside these parentheses. So this negative doesn't get squared away. Divided by 2 times negative 9.8 meters per second squared. Notice that the negative here will cancel the negative there. Yay! And then you plug in your values and you get a delta y, or your change in height going from here to here. And I believe you should have gotten, what, 25.8? Is that right? When you plug in your values? Okay, and this is part A. Now, there's another way of doing this, by the way. I think that one of the groups What you did, you started up here and you let it fall and you said it was negative 20. Well, I don't know. You could do it that way, knowing that the final velocity is equal to the initial velocity, but in the opposite direction, and then you can figure out what your displacement was. It would be a negative displacement. When you fall down, if you start up here and let it fall down, it's going to be a negative displacement. But here, we're going up. We're going starting here. My initial velocity, final velocity is 0 up at the top. Now, here's what the book is implying here. Now that we know what delta y is, we can we can solve for time here as well, and we don't need this value for delta y to solve for time because I know final velocity, initial velocity, acceleration, and I want to solve time, so I'm going to use the first kinematic equation and then solve for time. Is the final minus the initial divided by the acceleration. I'll plug in my values. This is 0 minus 22.5 meters per second divided by the acceleration, which is negative 9.8 meters per second squared. Now, what is 22.5 divided by 9.8? Can someone do that for me? Actually, I just found my calculator too. Divided by 9.8. 2.29 or 2.30, actually, if you round it off. Now, what is this time? When did 2.3 seconds go by? I mean, where are we in the problem? We're up here. So this was the time to go from the final velocity to the, from the initial velocity to the final velocity. It can be shown that to go from here to here will take the same amount of time. I'll show you in just a second how you can do that. But, so when the problem says, hint, the time to rise equals the time to fall, well, if the time to rise is 2.3 and the time to fall is 2.3, we just double 2.3. So we say the total time is equal to 2 times the 2.30 seconds, and you get 4.6 seconds. And that's my answer. T equals 4.6 seconds. Okay, now I'm going to show you an alternative way of doing this where you don't need to double this. We know the initial velocity, but here's what we know for the whole thing. Watch this, the whole thing. If the ball starts here and goes up and down, well, what is my delta y for the whole problem? If I start, if the ball leaves right here, goes up and down, here's my final y position. So my initial y position is right here. My final y position is right here. So what's my delta y? 0. So this is another thing that's kind of stated in the problem. It is stated in the problem, but they don't tell you that it's delta y. Delta y for the whole problem equals 0. Now what does that let me do? Well, it lets me solve part B in a different way. I don't know the final velocity here, but I am given the initial velocity, the acceleration, and the displacement. And I want to find time. What equation doesn't have final velocity in it? The third kinematic equation. So I'm going to use delta y equals v naught times t plus 1/2 a t squared. Now watch this. This is very cool. I'm going to solve this for time, but before I do that, I'm going to say delta y is 0 if I end up at the same height from where I started. So this is 0 equals v naught t plus 1/2 a t squared. Now, by the way, this right here, this equation, if you're going to solve this for time, and if there is a non-zero delta y, you have to use the quadratic formula. There's going to be 2 answers. But in this problem, well, there is two answers. When does all this equal 0? Well, one answer is when t equals 0, isn't it? I mean, at t equals 0, there's no delta y. That's a trivial answer. If you give me, well, t equals 0, I will not give you any points for that on a test. But I can now divide both sides by time. That cancels that and cancels that. So I get 0 equals v naught plus 1/2 a times t. I'm now going to solve for time. Time equals negative v naught, pull that to the other side, multiply both sides by 2, divide both sides by the acceleration. Now I can plug in my values. Negative 22.5, the negative comes from here. V naught is 22.5 meters per second. I'm going to multiply that by 2. And what is my acceleration? Negative 9.8 meters per second squared. And when I evaluate all this, I get t equals 4.6 seconds. So when you do it this way, you don't need to like figure it out for half the problem and then and then double it at the end, which is what we did over here. So either way of doing this works just fine. Okay, but what's the big idea? The big idea is this. There are more things given in a problem sometimes than they tell you. If a ball is thrown up and it goes up and back down and you catch it at the same time, well, you need to know, hey, I know what the acceleration is. We're on Earth and it's in free fall. Oh, it's changing directions at the very top. Its velocity is 0. Oh, I caught it at the same height that it took off. Delta y equals 0 at that point. Now, delta y up here is the maximum height. But delta y right here is, for the whole problem. And there you go. There's the whole thing. Let me fit it on the paper right here. Okay. And that's practice problem 32 on page 106. That is all.